Pearson Edexcel Further Mechanics 1 sample assessment paper. So based on this book here, sample for 2017, let's go straight into it. We've got a very easy warm-up question here. Impulse is mv mass mu. You're allowed to use vectors here if you want to, so we put those in. We of course sort this out, we put it on the other side to get this. We divide by 0.5, which means doubling. And then of course, kinetic energy is a half mv squared. The v refers to this speed if you're working with velocities. So let's find the speed of this and the speed of this, the initial velocity and the final one, by of course just doing Pythagoras. So this makes root 17, that's the initial speed, and then do it likewise here, sorry, not here, that's the impulse. Do it again here, that's the final speed. Then plug those into a half mv squared, of course the roots square out, which is nice. We get this as our initial kinetic energy, we get this as our new kinetic energy, we do this one, take away this one, and we get a very easy answer of 12. Excellent. Question number 2. Let's draw this inclined plane problem. Let's go. We've got a parcel of mass 5 on a plane, it's shoved upwards 14 meters, so it ends here. What an incredible job with PowerPoint I'm doing here. Look at that, representing this box moving and ending up here, starting here. Incredible. We've got a force going down of mg, which is just 5g. And of course we break that force into the little triangle that we're all very used to. This will be 5g cos theta, this will be 5g sine theta. We think about what this triangle actually looks like. Just know that if you actually find alpha in these questions, I think less of you. Like a lot less of you. What you need to do is just draw a triangle. This is opposite over hypotenuse. So think of a triangle with opposite 1, hypotenuse 7. What would the last side be? Well, 7 squared take away 1 squared is root 48 if you root it. So the triangle is the root 48, 1, 7 triangle. So cos theta alpha is going to be root 48 over 7. And tan alpha, which we don't need, is going to be something else. I guess it would be 1 over root 48, wouldn't it? Something like that. But it doesn't matter. We just plug in those two numbers into here. So cos alpha goes into there, that is a little bit awkward, but it's fine. Sine alpha goes into here, that's much more natural looking, which is good. And then of course, because this is a frictional problem, we have a rough slope. We need the reaction force, which is just the same as this, that goes there. And then the maximal friction force downwards is just mu times r, so it's mu times this. We don't know mu, so I'll just shove a mu there as well, and that's the reaction force. Good, so I think we have all of our forces in here. Use the work energy principle to find the value of mu, which is the coefficient of friction. So what the work energy principle says is that work done is going to be equal to the change in energy. That's kind of what the textbook says. I know it's worded awkwardly, but that's just what the textbook says. So the work done is the frictional force times the distance that it was applying for. So it's going to be this times 14. That's going to be the work done, which I can just write as this. I've done some simplifying here. And the change in energy is going to be the change in kinetic energy. Now it starts with kinetic energy of, it's pushed at a speed, right? 8 meters per second. So it starts with kinetic energy half mv squared, where m is 5, v is 8, which is this, of course. And it ends with kinetic energy 0, because it's going to be at rest here. And then there's also another change in energy, which is the gain in potential energy. So if we draw a little triangle out here, like this, it's gained this much height. This is alpha because it's just corresponding angles. So this here is 14 sine alpha. Sine alpha is a seventh, so 14 times a seventh is just 2. And it's gained 2 in height. This is actually just the triangle we were thinking about earlier, times by 2, isn't it? Instead of hypotenuse 7, hypotenuse 14. Opposite side is 2 instead of 1. Anyway. Gain in height of 2, which means its gain in potential energy is m, which is 5 times g times 2, which is 10g. And that's the change in energy, right? So 160 take away 10g must be equal to this work done. And we say that g is 9.8, we can plug that in if we want to, and we can of course just solve this, we get this as our answer. So just one way the model could be refined. I mean, there's lots of things you could do. Just read through here and look for anything that we're assuming, and we'll pretty much be done. I said something like you could model the parcel not as a particle, but with actual, like model it with actual size. So there it is. So treat it as a particle. Let's not do that. Let's give it actual dimensions, and that would immediately make it a bit more realistic. Good. Question number 3. We've got a mass m on a smooth horizontal surface with 2 walls in between it. The m is right in the middle of them, so and the walls are 4 meters apart. Again, the m is modeled as a particle here, so that's exactly 2 meters to either wall, because we're not considering the size here. Okay, projected towards one of the walls, it doesn't matter which, it's going to be symmetrical, with speed u. So I just projected it that way with speed u. Coefficient is 3/4, and this is the formula, of course, for the coefficient. So therefore, the speed that this particle hits this, sort of approaches this wall is u, because the wall isn't moving. So the speed of approach is u. So therefore, if I times this by u, I get ue is equal to the speed of separation. but E is 3/4, so that means 3/4 u is equal to speed of separation, and therefore when it hits this wall it bounces back with speed 3/4 u. And we can do that again, right? And we can do that again over on this wall. I think first, just because I don't need to right now, I think first I'm just going to deal with this question here, which has the magnitude of the impulse on the particle is this. Now the impulse acts this way, and of course we saw this in question 1, I equals mv minus mu, and we know v, we know u, and m is going to be cancelling with impulse being lambda mu. Now the impulse is going in this direction, the impulse acts perpendicular to the wall. So if I call positive this way, which I regret doing now, but if I call positive going to the right, this is going to be a positive number, and this is going to be a negative number, and so is that. So I need to put a negative in front of this because it's going the wrong way according to my working. I put a negative in front of that, and I put a positive in front of that, which ends up it being a negative anyway. All the negatives will cancel, so I guess it doesn't really matter that I did that. But you eventually get that lambda is 7/4. Of course, the mu's will cancel as well. Good, so lambda is 7/4, and the impulse is 7/4 mu, I guess we can say. Sure, okay, I've written that down. Now we can get to this next bit. So just the same as we did to get from here to here, when this hits the next wall and you apply essentially another factor of 3/4, which makes the speed going away from this 9/16. And then we're going to look for the total, we know the total time it took to do this, and arrive back at its starting position is 7. And we want to find the value of u. Now, speed equals distance over time. We've got the time, so we're going to be solving for distance over speed. Distance over speed is time. Now, okay, so how long does it take to get from here to here? Well, the distance was 2, and the speed was u. So 2 over u equals the time it took to get from here to here. So total time, which I know is 7, is 2 over u plus the amount of time it took to get this way. Now, again, distance is 4 now, speed is that, so it's going to be 4 over that, plus the amount of time it took to get to here, which is going to be 2, the distance there is 2, remember, over this. And we know the total time is 7, so we can plug in 7 and we can start sorting all this out. Of course, the 4 goes up there, the 16 goes up there, cancels a little bit, I think, is what I did there. Yeah, 32 over 9. No, I didn't. 32 over 9 there. Times this one by 9, times this one by 3, and we get this. Add them all together, and we get this. So, and then I think, is there some cancelling to do? No, 7 equals that, times across, and divide through, and we get this as our value of u. Good. It really helps, and I'll say this again later on in the paper, it really helps that the 2019 paper had an identical question to that, literally identical. This is why past papers are important. It makes things very easy if you've seen the questions all before. Anyway, we've got another question which is again identical to something that was asked in 2019, this exact picture with a different angle. So we've got u here, this is a show that question. We've got e on this wall is this, and e on that wall is different, it's this. Just going to write it like this because PowerPoint makes this look a bit awkward, so I'm just going to write it like this instead. And we've got some stuff to do. Now, it's a show that question, so we need to do this from first principles. So we'll say that this distance here, or sorry, the component of this velocity here is u sine 60, sorry, and this one here is u cos 60. And now, of course, we know sine 60 is root 3 over 2, and we know cos 60 is a half, so I'll put that in there. Speed of separation over speed of approach is e. Now, when you're meeting in this kind of hitting a wall like this, the horizontal component parallel to the wall is unchanged upon impact. So this component is also u over 2. It's the same as this. Now this one is where this formula comes in. The speed of approach to the wall is this. So that I can plug that in there. E is 1 over root 3. And the speed of separation is therefore speed of approach times e. So this is just going to be speed of approach, which is this, times e. But of course, e is 1 over root 3, which cancels nicely here. So I end up with u over 2. So those are the components on the outward velocity. And now we can just do that game again, right? The inward velocity to this wall, the horizontal parallel velocity to this wall is just still this, because there's no friction as it goes across the floor. So this speed is equal to this speed. And likewise, this is the velocity perpendicular wall going into it. And then we play the same game as we did here, right? This velocity doesn't change, so this is still u over 2. And this component does change, and it changes with a factor of e. So it's this one times by e. Exactly the same as how this one was this one times e. So we just take this one times it by e, but e is different this time, it's this. Now, you could write that if you really wanted to as root 2 times root 2, which cancels with one of those root 2's, which makes a root 2, root 5 on the bottom, which I just wrote as root 10. And now we're looking for the final kinetic energy of the ball. Now we haven't got the velocity of the final part of this journey here. We've just got the components. So to find this, we're just going to do this squared plus this squared and square rooted. I mean, kinetic energy before is clearly a half u squared. So I'll just write that down. The speed afterwards, though, so the actual speed of this, using the components here, is going to be this squared plus this squared, which is this. Put them together, and we eventually get this. And now I can plug that into the formula to find the kinetic energy afterwards. The root obviously cancels. I just wrote this as a decimal like this, where I put a half mu squared out the front, because that's completely comparable to that. And now just a factor of 0.35 means that it's 35% of what it was before, which is what I was being asked to show. Cool. In reality, the floor and the walls may not be smooth. Well, if they were rough, they would slow the thing down. And if they slow this thing down, then the final speed is even less, which means there's even more percentage speed lost. So the amount of percentage left over is less. So more percentage loss, amount of percentage at the end is less, I guess. Yeah, sure. Cool. So say something like that. Good. Question number 5. Third question in a row. Both on the 2019 and the 2020 paper, there was a question where it was about a car moving on a flat road, part A, and then on a inclined road, part B. So probably revise this question because it's definitely coming up. This is what the picture looks like. And again, 2019 and 2020 were identical in that they asked about power here, because otherwise this would just be a regular mechanics A-level problem. Power is equal to force times velocity, so we take the velocity, which is 20, we divide it by this. This is 12,000 over 20, which is this. So that's our force in newtons going forwards. And now we just said F equals ma. There's no friction because all the resistances is lumped into here. I've just shoved V as 20 into there as well. So 600 minus 240 is equal to 600A, and we've solved for A, and it's very straightforward. Good, 4 free marks. Excellent. Now we're on a slope. And we have the force going forward of this. Now, I've written this as the force because they've told me the speed is W. So notice before I took the power, divided it by the speed to get my force forward. Here, I'm going to take the power, which is still this, divide it by the speed, which I've been told is W, and I just get this. Just again, applying this formula, putting it straight in there just because I didn't want to write it twice. And the force going backwards is, of course, this with W taking the place of V, because that's what I know the speed to be. Now, the only issue here is we have an extra force being applied here, which is the force due to gravity, because it says that the resistance that's lumped into here, all the resistances here, like air resistance, friction, and so on, do not include gravity. So let's make the gravitational one. Mg goes straight down. Do the same triangle we saw before, so mg cos theta is here, mg sine theta is there. Of course, we're told sine theta is this. I actually don't need mg cos theta, do I? So I don't need to think about a triangle that would be like this, because there's no mu r going on, so I just need the mg sine theta is here. Sine theta is 1 over 14, divide that by 14, we get this. And now we can just set equals F equals ma. Again, we have this, take away this is equal to m, which is 600, times the deceleration. Be careful, deceleration means that a is negative. Just be super careful to get that right. We put all this out, we plug all the numbers in, that's 9.8. We sort this all out, we times by w, to make a quadratic. We can divide by minus 2 here, I think, to get that. If you want to, you can be brave and try and do this without calculator. Not a good idea because it ends up being a horrible number. But yeah, just type it into calculator and you get your answer for W. Good. Question number 6. I think we've got 3 questions to go. We've got 2 spheres hitting each other like this. We've got vector of the first one 3, 3. Vector of the second one minus 5, 2. They meet along a horizontal line parallel to I, which is important because it means that the vertical components do not change. So this afterwards still has a vertical component of 3j, this one's still 2j. Let's just make up that the components for this one afterwards are ai maybe and bi, something like that. And then this shouldn't have all come up at once, but who cares? We set up the conservation of momentum, so 2m times 3, and we just set up in terms of horizontal movement. So 2m times 3, which is this one, plus 3m times minus 5. So this is the momentum before horizontally. 2m times 3 plus 3m times minus 5. Of course, the direction is important. Equals 2m times a plus 3m times b. That creates this expression here, cancelling out all the m's. And then we have the coefficient of restitution, which we again considered just horizontally. So b minus a is the speed of separation, divided by the speed of approach, which is 3 minus 5, which is 8, equals a quarter. 8 times a quarter, I believe, is 2. So we get b minus a as a 2. I think what I've probably done here is times this one by 2 and added them to get this, which gives me b as 1. And I already knew that the vertical component was 2, so that gives me a velocity of b of minus 1, 2. Cool. So that's all good. Find the nearest degree, the size of the angle through which the collision is affected. So, and this is this one. So we've got a -5, 2 going this way first. Then we've got a -1, 2, which goes this way. And we want to find the angle. You can do some dot product if you want to here. I didn't bother actually. I just broke out some triangles. This triangle by definition is 1, 2. 1 across 2 up. So the tan inverse of 2 over 1 gives me this angle. And then do the same thing here. We get 2 here, 5 here. Tan inverse of 2 over 5 is this. And then we can just do this, take away this to find the change in angle that we go through, which is this angle here. So the nearest degree is 42. Apologies for that all coming up at once, but I think it was okay. Question number 7. We have a ceiling with a string and then a weight at the end of it, distance sitting at D here, and it's in equilibrium, which means the force going downwards, which is just mg, is equal to the force going upwards, which is the tension, and the tension in elastic string is given by this formula, where lambda is the modulus of elasticity, which is this. The stretch is, if it's distance d, now it naturally sits at length a, so the stretch must be d minus a, I believe. It should be the extension. Naturally sits at length a, it's currently sitting at d, so the stretch is d minus that a there. Divided by a, which is the natural length. And so this thing must be equal to this thing, because it's in equilibrium. Those are the only two forces. Cancel out the mg's, times by a, add 3a, divide by 3, and we get d is this, which they were asking us to show. Good, the point A is vertically below, so now I think we've got a new picture, where it's now being held at distance of 2a down. Right, it's now being held at distance of 2a, so the weight is still the same, mg going down. The tension, I've now replaced this with an a, because the stretch is now a, right? Because it naturally sits at a, it's now at 2a, so the stretch is an a, so that's the extension. Good. And it's being released. So find the acceleration. Well, we just do F equals ma. So this minus this, the a's cancel here to just get 3mg. This minus this equals ma. All the m's cancel, and a is 2g. Very nice and straightforward. Next, find in terms of G and A the maximum speed. Now you can quote a result here, this came up in 2019 as well. You can quote a result here which says that you obtain maximum speed when these two forces are in equilibrium. So when T equals mg, that's when you have maximum speed. So what I'm going to do is I'm just going to draw a picture that looks like this. And I'm going to say, okay, there's going to be some distance, so let's just pretend that when this thing is x down from the ceiling, when the string is stretched by factor x, that equals mg. So I'm just going to replace this with an x, because I don't know where it is in the picture. It's somewhere up here, somewhere I presume. But I'm going to replace this with an x and say when that equals that, that's when it's at maximum speed. Of course, the mg's cancel, times by a and divide by 3, and you get x as a third a. So the picture looks like this. Right, it naturally sits at length a. When it's stretched by a third a, which is that extension there, that's when the forces are in equilibrium, and that's when it's at maximum speed. So it's at maximum speed right here, when it's 4/3 a down from the ceiling. Now, how is that useful to me? Well, now I set up an equation formula, an energy equation formula. So I say the gain in kinetic energy is a half mv squared. So let's pretend this is traveling at speed of v right now. It wasn't traveling with any speed first because it was being held at rest. So the gain in kinetic energy is just this. The gain in potential energy, mgh, is m times g times the rise. Now, it was sitting at 2a, now it's sitting at 4/3 a, so its rise is 2/3 a upwards, so mgh, that's the rise, so that's the gain in potential energy. And now there is a loss in elastic energy, right? The loss in elastic energy, well, right here, the elastic energy, using this elastic energy formula, so just remember these two formulas, they're not in the formula book. Previously, the extension was a, so replace that with an a, replace L with an a, obviously, and replace that with that, and you get this. That was the initial elastic energy that was in here. Now there's still elastic energy in here because you've still got a stretch of a third a. So put a third a into here, again put a into there, and put 3mg into there, and we get this. And now the gains in energy must be equal to the losses. So this plus this must be equal to these two things. So I'll write that down. I'll say this plus this equals these things. I've done a lot of cancelling a lot of numbers and a's here to get these two things here, so just make sure you follow how I got from there to there. Cancel out all the m's, yeah, all the m's, times everything by 6, I believe is what I did here, just for fun. Yeah, that looks like what I did. And then of course all these GA's go together, divide by 3 square root, and we get our fastest velocity there. Good. Find in terms of A the distance O to B. So this is slightly different again. B, if you read the whole question, it was held at 2a, it was let go, it went up, at some point we just found it was at maximum speed, and then it kept going up slower and slower until it arrives at instantaneous rest up here somewhere, as denoted by this thing here. And I'll just call this distance down to here x, and then I just need to find x because that's the distance from O to its finishing position B. Now there's a fair bit to do here, but again, energy equations are where you want to go here. Now it started at rest because it was being held at rest, and it's also finishing at rest because it's instantaneously at rest up here. It's throwing up here and then stopping instantly, then it will fall back down again. So there's no gain in kinetic energy. There is a lot of gain in potential energy, mgh. The rise in height is 2a minus x. So mg times this 2a minus x, that's the gain in potential energy. And there's also a lot of loss in elastic energy. In fact, it's lost all of its elastic energy. It previously had elastic energy this. This should say 3 over 2, I believe. Apologies for another mistake there. That should say 3 over 2. Let me just explain though. We already saw that the initial elastic energy was this, which is just 3 mg a over 2, which is what I'm quoting here. It should say over 2. I don't know where that fraction has gone. But loss in elastic energy is 3 mg over 2. And now it doesn't have any elastic energy at the end here because this is going to be flown upwards past the point, and this is just a string. So the string is going to be like loose here, right? So there's not going to be any elastic energy left in it. So the losses are all of what you started with, which should be this over 2. And now, of course, the gains and losses must be equal. So this gain in potential energy must be equal to the loss, which should be 3 over 2 in elastic energy. And we get this here times by 2. In fact, what have I even done here? Cancel out the mg's, of course, sorry, yeah. And then we can just move the x over here, move this over here, and we get x as a half a. And that will be the distance there. Good. Last question, I think now. Got two particles, 2m and 5m, moving towards each other with these speeds. And we set up the same two equations we did last time. So let's just pretend this is going with speed v this way and w this way at the end. Now, we're told that the motion of q, which is this side, has reversed. So I know w is a positive number if I'm drawing it like this. Not so sure about v, but w is definitely a positive number. Now we set up the same two equations we always set up. So conservation of momentum says that this times this plus this times this must be equal to this times this plus this times this. Just be careful to get your negatives right. This is going in the wrong directions. That's negative. I'm not so sure about these, but that's okay. So let's put all that in. We get this. And now formula with E, speed of separation, which is w minus v in my picture, is equal to 2u minus u, which is 3u. Sorry, minus u is 3u equals E. Times everything by 3u, we get this. Solve for w and v. So I think I times this one by 2, everything here, times this by 2, so that I can add them up to get this. And then go back to the original equations and times this one by 5, I presume. Yeah, and again, I think I chose maybe to do this one minus this one. Yeah, this one minus this one will get me 7v is equal to this. So, and now remember, u is positive because it's I've chosen that to be going in this direction. So u is definitely positive. E is strapped between 0 and 1, which means this is sort of trivially negative. So v is definitely going this way, and that's fine. All of these values are negative, so v is definitely going this way. W, not so sure about. I need w to be positive, though, for my picture to work. So I need this to be greater than 0. Cancel out the u's because they're not 0. Add 1, divide by 6, and we get this. And so E is between 1, which is the maximum it can be, and 1/6, which is the minimum for W to be going in this direction. Good, that's the most of the question actually done here. Just going to take this result and put it underneath here, and this result put it underneath here, like this. Show the kinetic energy lost is this much. Now I know E is a third now, so let's plug in a third into here. Or into here first, I guess. This gives me 2 of them, minus 1 of them is 1 of them, and that divide by 7 to give me this. And here, plug in a third, get 5 here, minus 1 minus 5 is minus 6, divide by 7, get this. And now I just need to do kinetic energy before is a half m times this squared, plus a half m times this squared, which is just this. The negatives don't matter anymore because I'm just going to be squaring them out anyway. I get this. Afterwards, it's going to be a half times this squared. Again, the negative's not going to matter. Plus a half times this times this squared. Just deal with this. Put it in the calculator if you want to. You don't need to do as much work as I'm doing. Divide by 7 here to get it over 14. Times this one by 7 to get this. And now that's the initial kinetic energy. That's the final. Do this, take away this. And we get this, which divides by 2 to make that. And without any further calculation, state how the kinetic energy lost would change if E was bigger. If E is closer to 1, you get a more ideal, more elastic collision, which means less energy would be lost. And that's all you need to say. I think that's the entire paper. Thank you so much for watching, and I'll see you next time.